Welcome to our OpenSim webinar. My name is Jennifer Hicks. I'm the OpenSim Research and Development Manager, and I'll be serving as the moderator for the webinar today. Today's presenter, Matt Millard, will describe the new muscle models he's developed in OpenSim, which will be included with our upcoming release of OpenSim 3.0. OpenSim is a freely available software application for visualizing musculoskeletal structures and simulating movements of humans and animals. The application includes tools for general purpose inverse dynamics, optimization to estimate muscle and joint forces, methods to create simulations from motion capture, and tools to analyze and visualize the results of these simulations. The first goal of our webinar series is to showcase cutting-edge research that is being performed with this software. OpenSim is also a growing and geographically diverse community of users. So the second goal of our webinar series is to provide an easy platform for the OpenSim community to communicate and collaborate. Before we get started, I have a few reminders about the webinar format. Questions will be addressed at the end of the presentation using the Q&A panel. If you need additional technical help, you can consult the guide on our website. And now I'd like to introduce Matt Millard. Matt is a postdoctoral scholar in the SimBios program here at Stanford University. He's an expert in multi-body modeling and simulation, skills he's applied to improving our existing muscle models and developing new ones. And with that, I'll pass it over to Matt.
Thank you, Jen. I'd like to thank OpenSim, SimBios, and Stanford for support during this work, and now we'll get on discussing the new muscle models in OpenSim. To provide you with some motivation, one of the main reasons this presentation is being given is that there are differences between the muscle models and they can affect your simulations. This is best shown with a forward simulation of a standard upper arm model that ships with OpenSim called the ARM26 model. In the animation you're about to see, all of the muscles have been turned off, and the only difference between these four models are the muscle models. And you can see that the elbow angle is different in all of them, and in addition, some of them are oscillating a little more than others, with the quietest model being on the right. These differences are occurring because the models are different. So on the far left, there is the Thelen _deprecated model, and on the far right, the quietest model, it is the Millard 2012 acceleration muscle model. So a lot of changes have happened since OpenSim 2.4. In OpenSim 2.4, we had four main muscle models. We had the rigid tendon model, the Delp 1990 model, the Schutte 1993 model, and the Thelen 2003 model. In OpenSim 3.0, we still have the rigid tendon model, and we still have the Delp, Schutte, and Thelen models, but they have had the word deprecated appended to their names. And we have three newly implemented models. We have a Thelen model, an equilibrium model, and an acceleration model. Why have these changes been made? The models that have been marked with the word deprecated had some minor implementation errors, and the word deprecate, for those of you who haven't heard it before, means to warn of future obsolescence. The new models have corrected these errors and also offer some practical and technical improvements. The presentation will have five main parts. It will begin with a small primer on muscle modeling to help you better understand the contents that follow. We will then discuss the improvements that have been made to the Thelen 2003 muscle model, as it's one of the most popular models in OpenSim. We'll show the differences between the new and the old using a benchmark simulation, and then we'll have a short discussion on how these changes may affect your results. The new models will then be discussed, beginning with the curves that have been used to define them, with a short discussion on the improved formulations of them, and again, you'll be able to see the differences with some benchmarking simulations. We'll then go through how to use these new models in OpenSim, and we'll finish with a summary. So to begin, let's go to the muscle modeling primer. The kind of muscles that are modeled in OpenSim look like this. That is, they have short, long tendons, and the muscles attach from point to point. The kind of muscles that are more represented or better represented as a fan, like your latissimus dorsi, are not modeled in OpenSim. We model these point-to-point muscles using a lump parameter muscle model. And because it's lumped, we can put all of the tendon on one side. And the part in the middle is represented by essentially one large sarcomere. So this is comprised of an active contractile element, also a passive contractile element. And these elements act at an angle to the tendon, given by the pennation angle. For those of you not familiar, muscle is often modeled as being incompressible, which means as the fibers shorten, their path has to change, and this is modeled using a pennation angle. Now, the tendon and the contractile element all have dimensions, and now we're about to go in and actually look at some of the equations that are used to model how muscle behaves. These equations are not to intimidate you by any means, but merely to show you what some of the practical problems are of muscle modeling. So the first assumption that is often made in muscle modeling is that the fiber force along the tendon is given by this equation. Now this equation has the active part of the fiber that was in the box on the previous slide, and the passive part of the fiber. And this is the parallel elasticity. And as you recall, this acts at an angle to the tendon. So this equation shows you the force that the fiber develops and applies along the tendon. Each of these symbols shown in bold are curves or even state equations. So here, activation is actually a state equation. And here we show the derivative of activation with respect to excitation. And this is at different states, that is, different values of activation, where activation of 1 is shown in red and activation of 0 is shown in blue, activation being 0, meaning that the fiber is totally off. The muscle fiber is able to generate force, but it changes as a function of its length. So here we have the normalized length of the curve, of the fiber shown in the x-axis, and the scaling of the fiber force according to the active force length curve on the y-axis. And here you can see the fiber can't really generate much force when it's at half of its normalized length, nor at 1.5 times its normalized length, and it generates force best at its normalized or optimal length of 1. The same is also true. We have characteristics that affect how the fiber is able to generate force as a function of its normalized velocity. So here, when the fiber is not contracting at all, it is able to generate its a normalized force of 1. When it's getting longer, that is, when it's stretching, it can generate more force. And when it's shortening, it can generate less and less force until it reaches its maximum contraction velocity, in which case it can't generate any force. The parallel elastic curve shown here, and this curve shows that the parallel elastic element engages when the normalized fiber length is greater than 1 and reaches a value of 1 maximum isometric force, or 1 FISO, at a strain of 60%. So, to put this fiber equation and to add a tendon to it, one of the first things that is made when you join these two elements together are that the inertial forces of the muscle are negligible. These inertial forces are the forces of acceleration acting on the mass of the muscle. This isn't true generally, but these forces are relatively small for muscle. So now we have an equation where we have the force that the fiber applies to the tendon subtracted from the force developed by the tendon as it's stretching is equal to 0. This equation is then massaged to isolate this value. And when you have that value, you can actually simulate using integration. So here we have the equation for the normalized fiber velocity. The terms in red are in red because they can cause singularities, or they can cause the term, this equation on the right, to go to infinity, which is very difficult for integration. So a number of other assumptions have to be made to make this equation practical to use. So the next assumption is that the pronation angle cannot go to 90 degrees, which means that cos phi has to be greater than 0. We also assume that this denominator here, product of activation times force length, is greater than 0. In general, this isn't true, but it's convenient and it can be closely approximated. The final assumption is that this equation is invertible, and over most normal operating ranges, that's okay. So now that you understand a little bit about muscle modeling, we can proceed to talk about some of the changes that have been made to the Thelen model. So first, we'll review some of the things that were wrong with the old model. So one of the good things was that the active force length curve was implemented correctly, and this is important because this is one of the most critical things to get correct in a muscle model. There were a number of small errors in the tendon force length curve activation dynamics and initialization, which may or may not cause noticeable differences in your simulation results. And then there were some large errors in the fiber force length curve and the fiber force velocity curve. Again, these may or may not affect your simulation results. So in OpenSim 3.0, we've corrected these errors, and we've offered some capabilities to manage these singularities that I mentioned earlier. So if we look at this equation again, terms in red can cause model singularities, and previously these were handled all internally to the model, and there was no option to change these. So now you can define a lower bound on activation. For some users, it's critical to be able to control this to a low value. We also have slightly changed the formulation so that fiber length does not reach a lower bound that causes a singularity. And we've also defined a user-defined maximum settable pronation angle. And finally, the force velocity curve that we've slightly changed it just near the end so that it is always invertible. We've validated the physics in the sense that we verified that system energy minus work is conserved. We've improved the initialization routine, and what will be more important to most users is that there is now a very rich data set available when you use this muscle, because you can get access to all of the intermediate quantities, such as the potential energy stored in the tendon, the mechanical power of the fiber, etc. These differences are best shown with a benchmark simulation. So we're going to do a sinusoidal stretch constant activation simulation of a single muscle. It is a pinnated muscle, as shown in the figure, and it has these properties. The fiber length is 10 centimeters long. The optimal pronation angle is 30 degrees. The tendon slack length is 20 centimeters. And the maximum isometric force is 100 newtons. And we're going to do a small stretch for this simulation, so it's only going to be 10% of its fiber length. And as you can see in the video, this is a very modest stretch. And if you look at the results of fiber velocity and muscle force, you will see some differences between the old Thelen model, which is shown in red, and the new Thelen model, which is shown in blue. These differences are only noticeable at the beginning, and at the beginning, they have different values because the initialization routine of the old model assumed that fiber velocity was 0, and the new initialization routine actually finds a fiber velocity that will give you a fiber force that has no big changes at the beginning. And this translates to the whole muscle force. So the whole muscle force in the new model, shown in blue, doesn't have a very big change in the beginning. It looks nice and smooth, whereas the old model had a big transient. Now, if we look at another simulation, this time with a larger stretch, we can see some of the other effects of the other changes that we've made. So this is a fairly aggressive simulation. We're changing the fiber length a lot in this simulation. Now, if we look at the same two plots, where the old model is shown in red and the new model's results are shown in blue, you find that as the old model approached a pennation angle of 90 degrees, it ended up doing some interesting things. The new model, when it approaches a pennation, well, its maximum pennation angle, the fiber length is actually clamped, and the tendon is allowed to go slack. And that gives you this nice zero velocity plot here. The other difference that you'll see if you do such an aggressive simulation is that the new model develops greater muscle force. And the reason why it develops a greater muscle force is that the parallel elastic element has now been implemented to be consistent with a Thelen 2003 paper shown below, and it's an exponential. The old model had a linearly extrapolated exponential, which was not consistent with the paper, and it developed less force. So now we'll discuss what the effect of these changes might be on your research results. So in your simulations, if you have small fiber strains and low fiber velocities, you'll notice that you have different initial conditions, and there might be as much as a 10% difference in force. If you have a simulation where you have large fiber strains and high fiber velocities, you will certainly notice a difference in initial conditions. You will also notice a difference in fiber kinematics as the pennation angle approaches or reaches 90 degrees. And you'll also notice a large difference in force as soon as your normalized fiber length exceeds around 1.6 fiber lengths or has a strain of 60%. Due to the differences in the parallel elastic element implementation. So now that we've talked about the upgrades to the Thelen model, it's now time to discuss some of the new model contributions to OpenSim 3.0. And we'll begin by talking about the curves that we're using to implement the muscle models. So the curves that are used now are C2 continuous. The typical curves that are used to model muscle are not C2 continuous. This is important for people doing particularly optimization. We've also tried as much as possible to make them physiologically accurate and, even more importantly, easy to edit. There are 4 new curves. There's a tendon force length curve, there's a fiber force length curve, there's a force velocity curve, and there's an active force length curve. The tendon and fiber force length curves look very similar to what you would see in the literature, so we won't spend too much time on them, although they are a little bit different because they are C2 continuous. The force velocity and active force length curves are different and worth looking at, so we will spend a little bit of time now looking at what they are. So here we have the force velocity curve as documented by Hill. On the y-axis, we have normalized force, and on the x-axis, we have the normalized fiber velocity. And this shows the concentric side of the curve. Now, the tendon force length curve, the C2 version that comes with OpenSim 3.0, is shown here. And this is the default curve, and it fits the Hill curve relatively well with some small differences here. But the new curve offers you some interesting capabilities. With the change of one number, you can turn this into an incredibly powerful fast twitch muscle if you want, or you can change it so that it's even a weaker slow twitch muscle. And by changing that one number, you can also make it in between these two extremes. This is true also for the eccentric side of the curve. And the two numbers that you would change to affect these different curve sides are a parameter called concentric curviness, shown in blue, and eccentric curviness. And changing concentric curviness will affect just the concentric side of the curve. And again, it will allow you to make either a really gifted fast twitch muscle or a really slow twitch muscle. And you can also make the same kind of changes with the eccentric curviness side. There are also four other parameters that you can change, but it's unlikely that you would need to change those much for your simulations. Another curve that's worth looking at is the active force length curve. So here we have the active force length curve that you might see if you open Nagin Herzog's book. On the x-axis, we have normalized fiber length, and on the y-axis, we have the active force length multiplier. So this curve tells you how well the fiber can develop force as a function of its length. Now, the active force length curve that's used in the Thelen model and in many other muscle models looks something like this. And over this range, the blue curve might approximate what the sarcomere does pretty well. But when you get to the extremes of the fiber length, say at 50% strain or 150% strain, this curve is really quite optimistic. So we've actually elected to make our active force length curve, at least the default one, fit what you'd get from a sarcomere. And we've done this because of this recent paper has done a test to find the active force length curve on a whole muscle and found that it was accurately modeled. That said, if you do want to change the curve, it's possible. And the parameters that you can change they're all shown here. The ones that you would probably be most interested in changing are the minimum active fiber length. So that's where this curve starts. You might also want to change the maximum fiber length, maximum active fiber length here. That tells you at which point the fiber really stops developing the ability to generate force. And then for some model formulations, particularly equilibrium muscle models, which we'll talk about later, you also might want to adjust the minimum value. There are also parameters to control where this shoulder is developed. It's called the transition fiber length. And you can also control the slope of this curve using the parameter, the shallow ascending slope. We've also improved the formulations, not just the curves. So there are two new models. There's a Millard 2012 equilibrium model. So you have improved characteristic curves, as I mentioned. But we've also changed this so that the fiber lengths that this model is able to generate are always realistic. That is, that the normalized fiber length is approximately always greater than half the normalized fiber length. It actually stays greater than the minimum active fiber length that you pick when you set that curve that we just discussed. The acceleration model gives you these improvements as well. So you get the improved curves and you get realistic fiber lengths. This formulation has no singularities, which importantly means that you can set activation to 0. This will be important for people doing finger and upper arm simulations. And this model is particularly well suited for dynamic simulations. These two models are documented in a conference paper, and they will be documented in an upcoming journal paper as well. The differences between all of these models are best shown with some benchmarking. So again, we'll do a simple single model benchmark, and we'll do a sinusoidal stretch constant activation simulation. But this time we're going to do it with a model that has no pennation. And otherwise it has the same kind of parameters. And we're going to do a large, slow stretch, and that's best shown in this animation. And if you look at what the Thelen model and the two new models produce, you will see a difference in fiber length. So here we have the plot of fiber length. This is normalized fiber length shown on the y-axis and time shown on the x-axis. And the important thing to note is that the Thelen model shown in blue is able to achieve a fiber length of 0. This is the new model because it does not have anything built into it to prevent the fiber length from going shorter. Whereas the two new models basically stop contracting when they reach the minimum active fiber length, which for this simulation is around a half normalized fiber length. Another thing that you would notice is that there's a difference in computational cost between these models. So here on the y-axis we have integration steps, and here on the x-axis we have activation. So this plot shows the computational cost associated with each model during this simulation as activation goes from maximally activated down to completely off. And what you notice with the Thelen and the equilibrium model is that they become more and more expensive to use as activation goes low, and they cannot reach zero activation because, as you recall, that causes a singularity in the fiber velocity equation. The acceleration model can go to an activation of zero, and more importantly, it actually becomes less expensive to use as activation goes closer to zero, and somewhere around, at least in this plot, and for this simulation, an activation of about 0.4, the acceleration model actually becomes cheaper to use. We've tried this also on real biological data, if you will, using both static and CMC. And the benchmark results that I'm going to show you now briefly are for the standard walking data and the standard walking model that comes with OpenSim. And the model is called Gate 2354, if you happen to look in the examples folder. And if we look at some results, here we have on the left side, we have the fiber force developed by the vastus muscle using the static tool. And on the right, we have the muscle force developed by the same muscle, the vastus muscle, but again, solved by the CMC simulation method. And the important thing to note is that the trends, at least for this muscle, are very similar. So you may or may not see very big differences if you're doing this kind of inverse solving method. If we look at a different muscle, if we look at the soleus, you will see a little more differences between the methods and the models. In the static case, the Thelen model is different from the acceleration and the equilibrium model because they have different force length and force velocity curves. In the case of CMC, these results are a little bit harder to interpret because CMC has got its own level of complication. So these differences are not just due to the muscles. Now we'll proceed with a model demo. So there are a number of different ways to incorporate these models, muscle models, into your musculoskeletal models. If you want to add these to your existing models, you can edit the OpenSim model file, which is in an XML model format, and just do a find and replace. And we can do that right now. So here we have the tug of war model.osim. This is a standard model file that's used, and you will see if you start to do any API programming. This is what the XML looks like. And if we look around, we'll find that there is a model, muscle model used in here already, and it is a Thelen model, Thelen 2003 muscle model. Now, if we simply do a find and replace, we can change the muscle model. And with that, we've just replaced the muscle model. Note that we can do this because all muscle models share 4 architectural properties: the fiber length, the tendon slack length, the pination angle, and the maximum force at isometric traction that they develop. All of the other muscle-specific parameters are ignored. So we just did a demo of editing in XML. You can also edit, once you've changed the muscle model, that is, you can open up the model in the GUI and edit the properties in the GUI. So again, using the standard API example of the tug of war model, we'll open OpenSim. And just to explain, tug of war probably will make more sense if you look at the graphic. This API example has a block that's being pulled on by a muscle on one side and a muscle on the other, and they're playing tug of war with the block. Now, the muscles used in this example that I've just opened, you can actually see which muscles are being used by opening up the force bar and then opening up the muscle tab as well. And if we click on muscle 1, you can see that it is an equilibrium muscle. And if we scroll down, we can see all of the usual parameters that you might see, like the maximum isometric force, the optimal fiber length. And if we go down, we can see that there are some other objects here that have not been present before. So for instance, there's a first order activation dynamic model. And if we click on that, we can change the activation time constant, deactivation time constant, and the minimum activation value. And this kind of setup is also true for the active force length curve. So if you wanted to edit any of those parameters that I just talked about, like the minimum active fiber length, you could edit these here. The defaults have been set up to match that curve as closely as possible. And you can do the same with all of the other curves as well. You can also easily make these changes from the API if you're a C++ programmer. So before you open your OSIM file, you can type in the command object rename type. In this case, rename a Thelen 2003 muscle to a Millard 2012 equilibrium muscle. This is equivalent to doing a find and replace on your XML. And then you can edit the muscle properties using all of the get and set commands that are provided with the muscle model. So in summary, I think it's best to offer my rating system based off of my benchmark experience. So the rating system looks like this. A dash means it's not recommended. 1 star means you get a reasonable simulation time. 2 stars means you also get realistic fiber lengths. That is, you don't have to check the results after your simulation to make sure that your fiber length is not, say, 0. 3 stars means that, in addition, you can simulate 0 activation. And this is based on my experience with the sinusoidal stretch simulation, the gate 2354, the standard gate model, and also the standard upper arm model, the arm 26 model. So in the very first row, we have the deprecated model. It's not recommended because it has implementation errors. These may or may not affect your results, but again, this should be used. The new Thelen model gets 1 star for all of the different tools that you might use because it gives you a reasonable simulation time. However, if your movement is large enough, you might achieve a fiber length of 0, which is unrealistic, and you'd be forced really to go back and check your simulation results. So it only gets 1 star. The equilibrium muscle gets 3 stars for static. For CMC, it gets 2 stars because in CMC and also in forward, you cannot set the activation to 0 because it causes a null singularity. Due to the assumptions that are made in static, you can actually set activation to 0. And the Millard acceleration model gets 3 stars for static. For CMC, it gets a dash because it's actually really time-consuming to use. You can use this model, and I have in CMC, but it's much more time-consuming than the others. In forward, however, it's excellent. It's typically a bit faster than the other muscle models. The muscles vibrate a little less because they've got some damping in it, and you can achieve 0 activation. Thank you for your attention, and please send your questions, thoughts, and feedback to me. That is for any questions that don't get answered in the upcoming question period.
All right, thanks, Matt, for a great talk. Before we start the open question and answer session, I have a couple quick announcements, reminders. First, please fill out the survey that's going to appear in a pop-up window in your web browser when you exit the event. This will help us improve future webinars. We'll also make a recording of this webinar available later this week on our website. Also, I should note the muscle models that Matt described will be available in OpenSim 3.0. We've started beta testing and plan to release in the next month or so. Also, we'll have our next webinar at the end of September, which will feature this upcoming OpenSim release. So OpenSim and this webinar series are supported by several grants from the NIH, DARPA, and the EU, including an NIH grant that funds our National Center for Simulation and Rehabilitation Research. Information about the center, upcoming events, and other resources for the OpenSim community are available on our website. And now let's get started with the question and answer session. All the questions will be text-based, so you have to find the Q&A box in your WebEx main screen, and it may appear on the bottom of your right screen, or if you have a Mac, there's a green area at the top, and you go to Options, and you can see the Q&A panel there. Go to the Q&A box and type in your question, and make sure you select Ask All Panelists. So we'll get to as many questions as we can. Let me see if there are any coming in yet. I don't see any. So while we wait for more questions to come in, I'll ask a question. So you showed the movie of the passive arm hang at the beginning of your talk. Now that we've heard more about the muscle models, can you provide any insights about why there were those differences that we saw?
Yes, just to remind you, I could replay the video, but the main differences that you saw were due to the differing active force length curves. Let's see if I can pull it up. So the two Thelen models have a very generous active force length curve that allows them to generate even up to 10% of their maximum isometric force at a fiber length of 0. And that means that these muscles are able to also generate force while they're relatively long, as in this case. These other two models have an active force length curve that is not as generous, and they aren't able to generate much force when the fiber is very long, and so the arm ends up being a little more stretched out.
Okay, thanks. Now we have a question from Michael Harris. He asks, will OpenSim 3.0 be accompanied by an updated user guide or theory manual that explains the muscle models discussed today?
So at the present time, the documentation for the muscle models is in the Doxygen for the muscle models, and there's also the paper. Is there going to be more documentation in the user guide, Jen?
Yeah, well, you've done a bit of documentation in your Doxygen, and we can incorporate this and make that easy to find on our website, definitely. Yes, on the Confluence wiki, we can put info there. Yes, so that was a long response, but the short answer is yes. So while we're waiting for some more audience questions, I'll ask another question. Are there other particular examples, use cases that would highlight the need for the equilibrium model versus the acceleration model?
Sure. So if you're using CMC, for instance, the equilibrium model will give you a very similar solution, but in a far quicker time. So that is one reason to use the equilibrium model over the acceleration model. However, if you're doing something like a forward dynamic simulation, the acceleration model offers results that are a bit more realistic because there's some fiber damping, which means if you're simulating the upper arm or fingers, you don't see as much bouncing. In addition, you can also simulate zero activation, which for those small light structures is quite important.
Okay, now I have a question from Prabhav Saraswat. Apologies for the pronunciation. So what's the difference in muscle modeling for inverse dynamics and forward dynamics?
So it depends on which method you're using. If you're using, sorry, I should back up. There are two inverse tools in OpenSim. One is static optimization and the other one is CMC. In static optimization, there are changes to the muscle model made to solve it. And the first is it's assumed in static that the muscle force is in linear with activation. Now this means that the tendon is now rigid and it also ignores the passive element. If you use CMC, you get an elastic tendon and you get an elastic parallel element, and in addition, you also get activation dynamics. So there are differences in how the muscles are used and what assumptions and even equations are used depending on the inverse method you choose. Oh, and the end of the question was in forward dynamics. So all of the things that I just said that apply to CMC are also true for forward dynamics. So you get an elastic tendon, you get a parallel element, and you also get activation dynamics.
Okay, so the next question is from Trent Guess, and he asks, is it possible to combine multiple different muscle models in one simulation?
So yes, and in fact that is relatively common. I believe even in some of the examples that ship with OpenSim, you will find, say, one muscle model used for one shoulder muscle and another one used for a finger muscle. This is particularly useful to do to save simulation time. So for example, if you have many muscles that have really short tendons and they're very stiff, you can save simulation time by replacing them with rigid tendon models. But for the one or two muscles that you have that have elastic tendons and you want all of the dynamics, say like the plantar flexors, you can use a more elaborate and computationally expensive muscle model to get those additional phenomena.
So now a question from okay, I'll ask another question while we're waiting for a few more to come in. So you showed static optimization and CMC results for Soleus and VASTI, and one of the VASTI intermediates matched a little bit better than Soleus. Do you have ideas about why there was a better match with VASTI in terms of where it is on its force length curve for the simulation you were looking at, or anything else that might affect those differences?
That's a good question. Here we, just to echo Jen, her question, she said, in the Gate 2354 walking simulation for static and for CMC, the three different muscle models produced rather similar results. And in the Soleus, the results were a little different. And I think the main reason why is actually related to tendon compliance. So here in VASTI, the tendon is not very compliant. It doesn't stretch too much. And the main differences that we see are going to be due to the active force length curve and the force velocity curve. And because the fiber, I believe anyways, is operating in a range where the differences between the Thelen active force length curve and the one that's used in the new models is not that different, you don't see very many differences. On the other hand, the Soleus has a very stretchy elastic tendon, and its fibers are shortening through the range where these active force length curves are different between the models. I think that's one of the main reasons why they're different. But there's also all of this a little high-frequency oscillation that's present on the equilibrium models. It's not present on the acceleration model because it has damping, and that makes me think that there's some interaction between CMC and the muscle models that's causing a little bit of undesirable chatter.
Okay, thanks, Matt. Now a question from Masood Malkutian. Can you explain and get some more details about the good, bad, and ugly slides, so the ones with force velocity and force length curve?
Sure. Let's see. The fiber force length curve that was originally implemented had a linear extrapolation after a fiber strain of 60%, which is the value that's typically used as the strain at which the fiber develops one normalized force. What's documented in the Thelen 2003 paper that I referred to a little earlier, they don't use a linear extrapolation. They use an exponential for that entire curve. So the differences in the fiber force velocity curve, let's see, I think I have a plot I can show you. So there were discontinuities here that caused some problems. That curve is supposed to look like this if you re-implement the paper. So yes, there were some differences between the paper implementation and what was in the original, or sorry, not in the in the OpenSim 2.4 implementation.
Okay, now a question from Prabhav Saraswat. Are you considering implementing a 5-component model that includes mass and viscosity?
So actually, it has been implemented. I certainly haven't had quite the time to go into all the details, but if you look at this conference paper for now, it will detail the formulation of this model, and indeed it has mass, a small mass between the tendon and the fiber, and it has damping, and the damping has been carefully chosen. There's nonlinear damping on the elastic elements that's similar to what you would see in a Hunt-Crossley contact model, and a light amount of linear damping on the fiber directly, and this allows you to have a model with mass in it that doesn't vibrate, doesn't have large transients, and also results in a reasonable simulation time.
Okay, well, we'll wait for a couple more questions, and I'll ask another one. So you compared the different models, and you talked about you had your star rating system, and you've talked about differences in computational efficiency. What is the scale of those differences in computation time for, say, a gate simulation or something like that?
Well, it would be like an order of magnitude. So at the moment, CMC with an equilibrium type model, it might take a minute to process a second of data, and the acceleration model, I believe, usually I just let this run when I went home at night, but I think it's somewhere around 10 minutes, which is pretty inconvenient.
Okay, thanks, Matt. You have a couple seconds to get in any last-minute questions. Otherwise, we'll go ahead and wrap up. Okay, yes. So thank you for the great discussion and all of your great questions, and Matt for doing your best at answering them. But that's some exciting results, and we'll look forward to a paper discussing them. In closing, we ask that you complete the survey that's going to appear when you leave the webinar, so that we can improve the webinars, and choose upcoming topics for future webinars. So thank you all for participating, and we hope you'll attend future webinars and continue to stay involved with OpenSim.